All right, this is the last section for the course. We're going to do 6.3, and this will cover trig functions at any angle. So last time we had it where we only dealt with the first quadrant, which was just between 0 and 90 degrees. Now we're going to expand out to the whole unit circle. And one thing that we're going to do to help with that is we're going to use what are called reference angles. And that's going to be where we try and put everything in the 0 to 360 degree context. Or 0 to 2 pi, depending on if you're using degrees or radians. And then last thing, we're going to do some relationships between trig functions. Some we kind of mentioned in passing, and this will just kind of be a little bit more formal, and some will be a little bit new. So one thing to keep in mind, this is the unit circle once more, but one thing we're going to do today that's going to be useful is we're going to start identifying these by quadrants. So, and I don't know why this is just one of those things that seems to have stuck, are using Roman numerals to identify the quadrants of the unit circle. I don't know why this is still kind of like mainstay, but it is. But the one thing to keep in mind that we're going to try and do is what are the signs of, well, sine and cosine. Since, I'll write over here, since if you have x and y on the unit circle, that's cosine of theta and sine of theta. Then you need to know, is sine positive, is cosine negative, things like that. So the nice thing though is if you know what quadrant you're in, you automatically know sine and cosine, if they're going to be positive or negative. So the first quadrant is nice because it's both of them are positive. And then the second quadrant, the x values are negative, but the y values are still positive. Moving down to quadrant 3, both of them are negative. And again, if you think about if you were to just plot any point, this would be a negative x and a negative y, hence why both of them are negative. And then the last one, quadrant 4, x values are back to being positive, and then y values are negative. So you want to be able to say, okay, I know what quadrant this is in because of the signs. And sometimes you might have to put some things together, because notice this doesn't really tell you 100% about tangent. Because remember, I said tangent was sine over cosine. So if you know that if tangent's positive, then you know it has to be in the first or the third, because positive divided by positive and negative divided by negative will stay positive. Versus if you know it's negative, you know it could be in quadrant 2 or quadrant 4. You'll typically have enough context to figure out what it is based on just those two things, though. So if we extend the function's domains, so given an angle theta in standard position, let x and y be any point other than the origin on the terminal side of the angle, and this is just the terminal side because we're talking about we rotate counterclockwise, and we define the radius to be the square root of x squared plus y squared. This is just coming from the Pythagorean theorem. So notice what changes here. This is not exclusively using the unit circle. Because here, notice sine is equal to y over the radius. Beforehand, we were just using that sine of theta was equal to y, and cosine of theta was equal to x. So if you're ever outside of the unit circle, then that ratio is going to change just a little bit. So just need to be aware of that. Tangent is nice though, because that's still just y over x. Because if you had y over r divided by x over r, that's y over r times r over x, which just still reduces to y over r. So tangent is kind of nice that it almost keeps the same thing from the unit circle. And so then, of course, cosecant, secant, and cotangent still have their respective pairings. And they're just the reciprocal of sine, cosine, and tangent, respectively. And really what it boils down to is sine and cosine are defined for all real numbers. So their domains are negative infinity to positive infinity. Tangent and secant are defined for all real numbers except the pi over 2 plus n pi. Now what that means is just you take a multiple of pi and add pi over 2 to it, because this is basically saying equivalently 90 degrees plus n times 180 degrees. Because remember, tangent is sine over cosine, secant is 1 over cosine, and if you think back to, here's your circle, then anytime you're on this line here, so this is 0 and this is the negative whatever the radius is. It would help if I could actually draw a semi-decent looking circle. And then here you're at 0 and positive whatever the radius is. So anytime you're at a 90 degree or 270 degrees or equivalently pi over 2, 3 pi over 2, that doesn't work. And then because you can keep rotating around the circle, you could technically go 360 and then another 90 and so on and so forth. And then because cotangent and tangent are, cotangent and cosecant are cosine over sine and 1 over sine respectively, anytime you're at a multiple of pi or 180 degrees, because that puts you either that was a cool error, not really, but you know, you're either here or here, which is going to be the radius in 0 or negative radius in 0. So anytime the y value is 0, cotangent and cosecant are undefined. Anytime the x value is 0, that's these, then tangent and secant are undefined. And then n just means it's going to be a whole number multiple. So like, you don't plug in a half, you plug in like 1 or 2 or negative 1 or negative 2, so on, like that. Alright, so first example is just going to be evaluate the 6 trig functions at theta equals 0, if at all possible. So, we need to pick a point along the ray defined by the angle theta, which equals 0. This ray lies along the positive x-axis, so any point on the positive x-axis will suffice. So easy one, hint hint, just use the unit circle if possible. Because you can always go back to sorry, you can always go back to you can always just go back to the unit circle, because anytime you let the radius be 1, that's a unit. Insert shape here. Square with side length 1, that's a unit square. Circle with radius of 1, that's a unit circle. So, and the other thing is, notice that these are kind of going to still work even if you hadn't used the unit circle. If we had been at the angle 0, which would be just this, then if we came out to a point, let's say here, and let's say this was, I don't know, 1.50, then you have x is 1.5, y is equal to 0, but the radius is also 1.5. So in this case, the ratios are going to work out very similarly to as if we had used the unit circle, just based on this. So this is just kind of an alternate way as opposed to using, just going straight for the unit circle and just pulling the values straight from there. So sine of 0, that's pretty easy. Remember we said sine is y over r. So y is 0, r is 1. So of course sine is going to be 0. Then if I do cosine of 0, I know that's x over r. So I'll write these over just for reference. So this is y over r. Cosine of 0 is x over r. So we have x divided by r, which is just 1 over 1. Or put more simply, it's just 1. And then lastly, for the first three, I should say, tangent of theta, or which is 0 in this case, which that's equal to x over y, or sorry, y over x. I'm getting ahead of myself and getting to cotangent, which again is just, if you think about it, you can do y over x, or you can do sine over cosine, whichever, which is again 0. Now if we go to sine's cofunction, that's where we run into an issue, because cosecant of 0 is undefined, because cosecant is the radius over the y value, which I keep writing x for some reason. So that one's out of the question. Secant of 0, that's a little bit nicer, because secant is going to just be 1 over 1. But remember, these are flipped, so this is now r over x, which is just 1. And then cotangent of 0 would be undefined as well, because it's equal to x over y. So this is just a way that you can see when you're just simply given an angle, then you can either look for a point that works, you can go to the unit circle. There's a lot of different ways to go about it. And you can see if we had picked another set of x, y, and r, the nice thing would have been that x and r would still come out the same, which means sine, cosine, tangent, and the rest are all still going to be the same values, regardless on if we had used the unit circle or if we had picked a circle with, even if we'd picked like radius 1,000. X would still have to be 1,000, y would be 0, and the radius would be 1,000. So just some interesting things to take note of for this example. So what if we want to determine the values of the 6 trig functions of this angle? So negative 5 pi over 2. Well, if you go to negative 5 pi over 2, which some people may be more comfortable dealing with it first in degrees. So let's see. So if we do negative 5 pi over 2 times 180 over pi over 2, or over pi, not pi over 2. So my calculator is so old, I have to hold it in the light like an old Game Boy just to be able to see it. Times 180 over pi. So this is equal to negative 450 degrees. Which when you look at it kind of makes sense, because you do, remember, if you go negative, then you go clockwise, and it goes a full 360, and then goes a little bit more. So if theta equals negative 5 pi over 2, this means we've rotated, and the easiest way is to look at it and say, okay, this is what we talked about by kind of narrowing things down to between 0 and 360, because here's 0 degrees, which is also 360 degrees, which is also 720 degrees, which is also 1080 degrees, and so on and so forth. But the reason that's important is it doesn't matter if I'm doing sine of 0, 360, 720, or 1080. It's still sine of an angle that the y value is 0. So sine of that angle is always 0. So first thing we did, like I said, you identify how the rotation went. Sorry, I thought I had more to it than that. But now, if you wanted to, like I said before, we can either go to your, what's the best way to put it? You can either go to the unit circle, or, so one other thing when you're dealing with these is you typically just want to see how many multiples of 360 degrees are there here. So I know that this is negative 360 minus 90 degrees. So the key takeaway is I can kind of throw out the 360 and say, okay, well, this is basically the same as if I was working with negative 90 degrees. So what I'm going to do, and notice I said it's basically the same, not it is the same. So 450 degree, negative 450 degrees and negative 90 degrees are going to have that same sine and cosine value. That's the key thing that I'm trying to take away here. So somewhere down here, this would be an x value of 0, a y value of negative 1, and because this is supposed to be our circle, our radius is equal to 1 as well. Because remember, the radius is equal to the square root of x squared plus y squared. And it's a radius. You don't have a circle with a negative radius. And so then we can go through, same idea. We're going to let x be equal to 0, y is equal to negative 1, and our radius is equal to positive 1. So when we do sine, we do y over the radius. We get sine is negative 1. Cosine gets us 0 over 1 because it's x over the radius. So we get 0. Tangent, well, tangent is y over x, but that's undefined, so we have to throw that one out. And then now, the nice part, we get to do the cofunctions, or the groups of cofunctions, I should say, because sine, cosine, and tangent are the main three, and then secant, cosecant, and cotangent are these kind of auxiliary but also useful measurements. They're just not, what's the best way to put it? They just don't usually get the chance to shine as much as, say, sine, cosine, and tangent, but you still do have problems that use them. So cosecant, that just becomes 1 over negative 1, because remember that's the radius over the y value. So that's just simply negative 1 still. Secant, well, that becomes radius over x, which is undefined, so no go for that one. And then cotangent, notice negative 1 over 0, that was undefined, but 0 over negative 1, I don't have the room to write it there, which is now x over, dang it, I almost got through all these without messing up. X over y, not x over r, which thus has a solution or an answer of 0. So sometimes you'll be able to find these in much easier ways. Some are going to take a little bit more, but you always want to be able to relate them to, all right, how many degrees have I rotated? And then what's the x value? What's the y value on that particular ray? And a ray is just like if you did like this. So this just keeps going, but then you can just pick somewhere to stop it and say, okay, I'm going to take this little, it took away my ability to write. It's going to let this little section here be the radius. And then wherever you stopped here, your x and y, you would get from the Pythagorean theorem that way. And again, you could use, here, I'm lazy, I take the easy way, and I just use the unit circle values, because making things be 1 or stuff like that just makes life a little bit easier, so that's the main reason I stick with those. You could, if you so chose, and sometimes you might actually have that, you might have just the x and y, and then you have to find the radius by using the Pythagorean theorem. And so it may just say, find sine of theta given x is this and y is this. And then it's your job to find the radius and then introduce, or then solve these just using the, what are the relations between the trig functions and x, y, and r. All right, so given an angle theta in standard position, the reference angle theta prime associated with its angle formed by the x-axis and the terminal side of theta. Reference angles are always greater than or equal to 0 and less than or equal to pi over 2. So basically, a reference angle is going to put them in this nice context where you kind of just throw it back into the first quadrant. Because we know how a lot of these things work in the first quadrant. Like I said, as somebody who's done more math problems than most people would care to do in their lifetime at this point, I still rely heavily on the first quadrant. So being able to put things back in that context is always nice. So let's find the reference angle with the angles theta equals 9 pi over 8 and phi equals negative 655 degrees. So, first one. So the terminal side of theta equals 9 pi over 8 is going to be in the third quadrant. So, specifically, we need to look at the negative x-axis. So what that means is I need to subtract pi from it. Now, if you look at this and go, okay, well, how did you know that 9 pi over 8 was in the third quadrant? Well, if I had 8 over 8, let's say 8 pi over 8, that's just pi. So 9 pi over 8 will just be slightly greater than pi. But I know it's not going to be greater than, this is 3 pi over 2. So, because I know this is greater than pi, in order to get the reference angle, which remember I said was going to be between 0 and 90, or between 0 and pi over 2, I know I have to subtract pi in order to get that reference angle. And if you go, well, this isn't in the third quadrant. Correct. Because this is theta prime here. If you were to turn your screen upside down, then what's going to happen is this third quadrant would appear up here as if it were like the first quadrant. But the thing is, now you have this reference angle that came from, or that's between now 0 and pi over 2 radians, which makes it a little bit easier to work with, because now you can say, okay, well, this is very similar to if I was dealing with the angle pi over 8. If instead of starting here at 0, 0 and rotating that way, I started here and kind of rotated this way. So it just kind of gives you a nicer context to deal with these. Now, phi of negative 655 degrees, this one's a little bit tougher, because this one is not quite as easy. It's outside of that initial 360 degrees of rotation. So in order to find it, we're going to have to actually add 360 degrees back to it. Because I need to, again, I keep using the phrase, you want to throw it back into the first quadrant. And you want to throw it into the first quadrant with the context of 0 to 90 degrees. Or in the other one's case, I needed to put it it was in the third quadrant, but I kind of got it in an angle that you can associate with the first quadrant. So, whoops. This is why I use a keyboard, because sometimes it takes away my ability to jump back and forth. So how do I get to this? Well, if I take negative 655 degrees, and I want to try and get a reference angle, then first thing I'm going to do is add 360 degrees to it. Which if I do that, so that gets me negative 295 degrees, which is actually the first kind of rotation backwards. So that's like, notice how this kind of loops through twice. I'm not quite there yet. This would be the negative 255 or 295. But I'm still not in the 360 degree range, or 0 to 90 range. So I'm going to add 360 degrees one more time, which that does get me the 65 degrees that I'm after. So now I have this reference angle in terms of a sine and a cosine, or sorry, not a sine and a cosine, in terms of between 0 and 90 degrees. So if it lands back in the first quadrant, then you need to do something like this, versus the previous one where it ended up in the third quadrant, so you actually had to subtract pi to kind of put it in that context of Well, if it were between 0 and 90 degrees, how would we treat that? And so that's one way, or those are two different ways that you find reference angles. One thing to talk about here is you may not know exactly how far it's going to take to get back to the 65 degrees. So you can always think that you can go between 0 and 360 degrees, and then you can go from 360 degrees to 720 degrees, and then so on and so forth. So to me, the easiest thing, though, is not to try and memorize, okay, how many times around the circle is this? Just say, okay, do I need to add or subtract 360? And then you go, okay. The main goal is going to be to get it into here, because once you have it in the context of negative 360, stuff like that, or between 0 and 360 degrees, then you can actually start to work with, okay, well, how do I find the reference angle? Which in this case worked out really nicely, because adding 360 degrees a couple of times, that got us back actually right into quadrant 1. So that made it a lot easier. So if it's negative, add 360 degrees. If it's more than 360 degrees, subtract 360 degrees until it's in this range between 0 and 360. Once you do that, you don't have anything else to worry about. Well, once you have it between 0 and 360 degrees, then you can actually determine the reference angle of putting it even in a smaller compartment of between 0 and 90. So now what if we want to evaluate these trig functions? Cosine of 7 pi over 6 and tangent of negative 225 degrees. So this one was nice because I've put this into the context of, yeah, because we found 7 pi over 6. Sorry, my brain. What? Yeah, sorry, I looked at it for a second and thought that I used the same numbers, and my brain stopped working for 2 seconds. So we don't know cosine of 7 pi over 6, but we do know cosine of pi over 6. And if you look at that and go, okay, how does cosine of pi over 6 help me when I'm trying to find cosine of 7 pi over 6? Remember throwing the things into the reference angle idea? Well, now what you need to look at is, all right, 7 pi over 6. Like before, that's, if I rotate to there and then subtract it from pi, or subtract pi from it, I get pi over 6, which is cool because I actually know how to deal with pi over 6. Because I know that cosine of pi over 6, if I went and referenced that, is equal to the square root of 3 over 2. However, notice an issue. This value is positive. We're in quadrant 3. Cosine's negative here. So that's actually just a really easy fix. Cosine of 7 pi over 6 is negative square root of 3 over 2. All I did was just throw a negative out in front of it. So first thing we did, we found the reference angle. I said, okay, well, 7 pi over 6 lands me over here. And then I need to make this angle theta prime, which now creates this new triangle, instead of trying to think about, okay, well, what is cosine of 7 pi over 6? 7 pi over 6 doesn't line up nicely here. If you go and use the unit circle, then you'd be able to find it on there a little bit quicker. But the reference angle idea is to kind of put in context why it works, not just... The unit circle is great, but it's a little bit dangerous because you do run the risk of, if you use it blindly without knowing why some of these things work, then you run the risk of not gaining the proper understanding, which is going to make some problems a lot harder, especially when you don't have those nicer angles to deal with. So this one's going to be similar to part A. I'm not going to try and I'm not going to subtract 360 degrees from it. That is another, or add 360 degrees from it. That is another way to think about it, but I want to use the reference angle idea again. So if we rotate negative 225 degrees, that puts us in quadrant 2. And then you've rotated here. This is a rotation of negative pi, or we're in degrees, so let me be more appropriate and say it's negative 180 degrees. So this one has the context of using the negative rotation followed by trying to get back to 180 degrees. If we go back to the previous example, notice the positive rotation, we went backwards again. That's how we're getting these reference sides. Is it's kind of like, okay, how far do I have to go back to get to this 180 degrees here? And so if we do that, this is a little bit easier. Because tangent of 225 degrees is equal to the negative tangent of 45 degrees. And if you go, okay, how do you know it's equal to the negative tangent? Well, the reason for that is over here, remember quadrant 2, this is a negative and positive, versus if I'm in Q1, I'm dealing with both of them being positive. So I know that tangent is positive here. However, when I come over to quadrant 2 or quadrant 4, these have mismatched signs. So I'm going to get a positive over a negative, which is going to give me a a negative value. So I put it in this context and say, okay, well, tangent of negative 225 degrees is the same as negative tangent of 45 degrees. Now, you can think about it in terms of odd and even functions like we did with the polynomials. Cosine, for example, is even. Tangent is odd. And so kind of what you're thinking about doing is almost like taking the negative on the inside and factoring it out to the front. So it's kind of like that idea. But it's easier just to think about it in this context of just don't think about it strictly mathematically, think about it logically. All right, if I do tangent of 45 degrees and this is my starting point, then I know what tangent of 45 degrees is. However, I should end up, because this should be a negative and positive value, I should end up with a negative value. But I know if I use 45 degrees, I'm over here, which means I'm not going to get a negative value. So to compensate for that, we're going to use just the negative out front, which gets you -1. And again, tangent of 45 degrees, you can get that from the unit circle because it becomes square root of 2 over 2 over square root of 2 over 2. And then because it's in the second quadrant, we have to put this negative out front. That's why it works out the way it does. If we had ended up in the third quadrant, then whatever our reference angle was, since both of these are negative down here, we actually wouldn't have to compensate with a negative here. Because once you get into Q3, like I said before, both of them are negative. So if you do negative over a negative, you're going to wind up with a positive. So you just have to be careful that when you're compensating for these values, you don't accidentally use way more than you need to. So cofunction identities are a nice way to, what's the best way to put it? Sometimes it's easier to solve sine of pi over 2 minus theta than cosine of theta. Same thing with cosecant and cotangent, using the cofunction identity to relate them. And notice this time, your cofunctions actually do get paired up, so that's actually a whole lot nicer than beforehand. So, and they're always pi over 2 minus theta, so, or 180 minus theta if you're in degrees. So these actually work out pretty well, and they're just kind of useful functions to have. Now, we talked about these reciprocal identities beforehand, but just want to refresh them. Cosecant of theta is 1 over sine of theta. Secant of theta is 1 over cosine of theta. And cotangent is 1 over tangent of theta. I don't know why when they were naming these, they didn't pair up. The only one that they paired up was tangent. So you got cotangent and tangent, but secant went with cosine and cosecant went with sine. I can't explain that, but it almost feels like it was an intentional way to make people confused. And then the quotient identities once more. Tangent is sine over cosine. Cotangent is cosine over sine. So if SOHCAHTOA doesn't work and you have sine and cosines, you can get to the rest of them from here. So we're not going to actually solve these, but we're going to verify the equivalence using the cofunction formula. So cosine of negative 5 pi over 11, that's going to be sine of pi over 2 minus theta. And notice it does turn out to be minus a minus. So it's actually going to be pi over 2 plus 5 pi over 11. Be sure you don't forget to distribute the negative to it. Which, find a common denominator, which in this case is 22. And you get 11 pi over 22 plus 10 pi over 22, which is sine of 21 pi over 22. So this is getting, because 21 over 22 is just slightly less than 1, you're talking somewhere, I don't know, maybe about here in terms of rotation for this one. Just kind of an example. So you at least know that sine would be positive. So cosine of negative 5 pi over 11 is equivalent to sine of 21 pi over 22. And cotangent of 195 degrees, because we're in degrees, we switch from pi over 2 to 90. And then we get tangent of 90 minus 195 is simply put tangent of negative 105. So, and if you took your calculator and put in these values, you would see that they do come out the same. It's really nice if you have a calculator that has a longer display, like a TI-84 or TI-83 or one of the nicer Casios, you could actually plug it in and it would display the value, and then you could plug in the next thing and it would display the value on the same screen. So you could compare it that way. So these are almost more like logic puzzles than trig problems. Given that cosine of theta is equal to negative square root of 3 over 2 and tangent of theta is negative, determine theta and tangent of theta. So cosine of theta is negative square root of 3 over 2. Now, if you go back to your unit circle, there's going to be a problem. There are actually two places where cosine of theta is equal to negative square root of 3 over 2 on the circle, which means you can't just pick one and go with it. So what we do is we kind of do this nice process of elimination. So what I'm going to do first is I'm going to say cosine of theta is negative. Now, where is cosine negative? So cosine of theta is negative in quadrant 2 and quadrant 3. So we know two possibilities for where cosine could be. Ow, my neck popped. And then if I go to tangent of theta being negative, well, I know for tangent to be negative, it has to be either in the second quadrant or the fourth quadrant. And as you can tell, we have a winner. Since cosine of theta and tangent of theta, the only place that they fall in the same, or the only place that cosine is negative and tangent is negative, is the second quadrant. That's where it has to be. So the nice thing is from this, we can determine, if you go back to your unit circle, now if you look where negative square root of 3 over 2 is in the second quadrant, you get that theta has to be equal to negative 5 pi over 6, or 150 degrees, whichever you want to do. And that means also we can determine tangent of theta, because that's equal to y over x, which more simply put here is going to be equal to 1/2 over negative square root of 3 over 2, which becomes 1 over negative square root of 3. And if you want to rationalize it, that becomes negative square root of 3 over 3. And you can kind of do this a little bit quicker because these both have the same denominator. So once those cancel, you're just left with 1 over negative square root of 3. Since this is 1 over 1 and this is negative square root of 3 over 1. So just kind of another way to think about it. Now, the other thing, so given that cotangent of theta is 0.4 and that theta lies in the first quadrant, determine sine of theta. So this one's not quite as nice. We don't know the angle. We just know it's in the first quadrant. So at the very least, we know sine's got to be positive. But how am I supposed to get values for x and y from this? Because I know cotangent of theta is supposed to be equal to x over y. But what do I do here? So we're gonna take the decimal of 0.4, which, to go back to how do you convert a decimal or to a fraction, remember you move the decimal place one place to the right, then you divide by 10 to however many places you moved it over. So like you think of like 0.004, you move it over 1, 2, 3. This is equal to 4 over 10 to the third because you had to move it over 4 places. So this is 4 over 1,000. And so fortunately, 4 over 10, that reduces down to 2 over 5. And now if cotangent is supposed to equal x over y, then now we have our x value and we have our y value. So then you go, okay, we're not quite there yet. You're correct, but we're getting close. Because we know that sine of theta is supposed to be equal to the y value divided by the radius. So now all we got to do is just find out the radius. Because I can put, this is my x, this is my y. I know it's in the first quadrant, so I can draw my triangle like this. And I'm going to draw this as well to indicate its right angle. And then you just use the Pythagorean theorem. And once you do that, you get the radius is equal to the square root of 29. Thus, since sine of theta has to be equal to y over r, sine of theta has to be equal to 5 divided by the square root of 29. And again, you can leave it as I wouldn't even call it an improper fraction. You can leave the radical in the denominator, or you can rationalize it whichever way you prefer. And so with that, we are done with not only the trig section for this course, but we are also done with the course. So I hope everything's made sense up to this point. And if this is your last math class, to me it's sad, but to you it's probably a happy moment, because I always think that math is always good to help you continue learning those critical thinking skills. But I know some people don't want to have to do equation after equation. So I hope the course has been good, and good luck with whatever comes next for you.